Okay, so in this video, we're going to talk about chemical equations. Okay, um, so chemical equations is basically an expression in which symbols and formulas are used to represent a chemical reaction. All right, and so it's more like a shortcut per se. So, like for example, you know, we can write, sodium metal reacts with chlorine gas to form sodium chloride salt. All right. That's long. Right? And can you imagine for every chemical reaction, we write that out. So we use what we call chemical equations. And chemical equations are just using chemical formulas to basically illustrate this very same thing that I just wrote, right? And so instead of writing all this, we could just say sodium, right? Metal, which is a solid, plus chlorine gas, right? It's used to make sodium chloride, which this is a solid. All right. And so let's just kind of dissect this and to make sure that we know what all this means. So when we're looking at this chemical equation here, right, on this right side of the arrow, we have what we call your reactants. Now, your reactants are basically, it's a substance that undergoes change in a chemical reaction and is written on the left side of the reaction arrow in a chemical equation. All right. And so these are your starting ingredients per se. Then on the right side, we have what we called the products. All right. Now, your products is a substance that is formed in a chemical reaction and is written on the right side of the reaction arrow in a chemical equation. Okay. And then this arrow basically just represents, that a reaction has taken place, what it yields, what is made, what happened, and so you could kind of look at it like this. So this is your whole chemical equation. Okay. Now, to make sure you understand chemical equations oftentimes illustrate the state of matter each of these substances were in the chemical reaction. So that you see what I've highlighted here, it tells us the state of matter that this specific substance is in. But let's go ahead and just make sure we list it all so that we know all the different ones that we typically see. So S stands for solid. All right. L stands for liquid. G stands for gas. And finally, AQ stands for aqueous. Now, I want to make sure we highlight two different things here. The difference between something that's a liquid and something that's aqueous. All right. Now, liquid simply means that substance is in its liquid state. Okay. So, like water, which is just the liquid state of H2O. And there's plenty of other examples, but it's in its liquid state. It's a pure form. Now, aqueous is something that's dissolved into water. Okay. So, that's something that's a little bit different. Okay. And so, oftentimes, you may have like particular substances, like say if we have NaCl and I write aqueous, that means this is really just salt water. All right. Salt that's dissolved into water. Okay. Versus if I wrote NaCl liquid, then that means this is basically a liquid version of table salt, like molten table salt, if that makes sense, right? But anyways, that's just the biggest difference between the two. All right. Now, when it comes to chemical equations, and one of the things I think hopefully you've noticed, maybe it was just like a question that came up in your mind, but it's like, okay, well, hopefully he gets to it later. But I'm going to just kind of rewrite the equation here so that way I could kind of address it. So, as I said, you have sodium metal, all right, with chlorine gas yields to make sodium chloride solid. All right. Now, hopefully, one of the things that you probably noticed when I was writing this equation was like, okay, I see the sodium metal, I see the Cl2, okay, and then when I wrote the products, I have NaCl. And so what you probably thought in your mind is like, okay, well, I see one sodium atom here, one or actually two chlorine atoms here, but on the other side, I have one sodium atom and one chlorine atom. What happened? Okay, first of all, where did the 2 come from? And then the next question is, why did this appear in the product side? Okay, so to make this, I'm going to answer both these questions. So the first question, where did the 2 come from for the chlorine? All right. So if you recall, there are several elements several elements that in nature, when you simply just say that element, it actually exists in pairs. Those atoms exist in pairs. All right. So like, for example, if I'm talking about the sodium atom is just sodium. It's just one Na. All right. If we talk magnesium atom, or we talk about magnesium in nature, it's really just Mg. If we're talking about silver, all right, the element silver, really it's just one atom of silver. But there are 7 elements, particularly if you mention their names, it's really, if you look at it from a microscopic point of view, these atoms are actually bonded together. They're in pairs. All right. And these 7 elements are bromine. Bromine always exists in 2. So if I say, hey, look at this sample of bromine, think Br2. Iodine, all right. Nitrogen, chlorine, hydrogen, oxygen, and finally fluorine. So these what we call are the 7 diatomic molecules, because in nature they always exist in pairs. So for example, when we say, hey, we breathe in oxygen, we breathe in O2. Okay. When we're talking about hydrogen gas, each molecule consists of 2 hydrogens bonded together. When we say, hey, most of the atmosphere is made up of nitrogen, we're talking about N2. All right. So this is basically why. All right. This is how they exist in nature. And so when I mentioned that, sodium reacts with chlorine gas, it's Cl2, because chlorine, like we see here, is a diatomic. Okay. Now, what happens when we go over here? Well, we have sodium chloride, right? Now, remember, that's an ionic compound. And so with sodium chloride, sodium is a +1 charge when it becomes an ion. Chlorine is a -1 charge when it becomes an ion. All right. And so it's a 1-to-1 ratio. So you own this for every one sodium, you have 1 chloride that is attached to it. All right. And that's what we see here. All right. Now, then I guess the question is, what happens to the other chlorine? Well, look at it this way, right? And so we have what we call the law of conservation of mass, which basically states that matter, or mass, right, cannot be created. That's an ugly B. I apologize. I'll erase that. All right. Cannot be created or destroyed. All right. And so if you start off with the chlorine, you need to end off with the chlorine. So what do we do in this situation? Well, right here is what we basically call a chemical equation that is unbalanced. All right. An unbalanced chemical equation is just an equation that does not meet the law of conservation of mass. Okay. And so our job as chemists, scientists, is to make sure that the equations all meet the law of conservation of matter. All right. And so how do we go about doing this? All right. Well, let's start with a clean slate here. So we have Na solid plus Cl2, which is a gas, yields NaCl, which is a solid. All right, so how do we make that this chemical reaction meets the law of conservation of matter? How can we make it agree? So what we're going to do is that we're going to actually write coefficients. What are coefficients? Well, coefficients is a number placed in front of a formula to balance the chemical equation, right? And these coefficients are typically used as multipliers, all right? And so what you got to do is you got to figure out, okay, what coefficient do we need in order to make sure this chemical reaction meets or agrees with the law of conservation of matter. All right, so I'll show you a way of kind of doing this. All right, and so basically what I would do to kind of figure out which coefficient do I need, I'm going to separate my reactants from my products. All right, because basically what you want to make sure for the reaction to be balanced, you want to make sure that you have the same number of atoms of each type of atoms on both sides of the reaction, right? So if you start off with 1 sodium at the beginning, you need 1 sodium at the end. If you start off with 3 chlorines in the beginning, then you need to have 3 chlorines at the end. Now, I mean, it doesn't have to be that specific number, but you have to have the same number of each on both sides. Because remember, atoms, matter, mass, it cannot be created or destroyed. All right, everything just gets rearranged. Okay, so what we're going to do for the reactant side. All right, so for my reactant side here, I'm going to count up how many of each type of atom I have. So I'm looking at sodium, and I see that I only have 1. Okay, and then I'm looking at chlorine, and I see that I have 2 atoms of chlorine. Okay, now I'm going to go to my product side. Now my product side, I'm going to count up how many of those same type of atoms I have on my product side. And I typically like to keep it in the same order. It's just easier on the eyes. So here for sodium, I have 1 sodium, all right, because there's no subscript there, so it's assumed 1. And then for chlorine, I have 1 as well. Okay. So now my job is, now I can see this in a little bit more clearly. So I say I have 1 sodium, 2 chlorines, 1 chlorine, right here on the product side. Okay, so now what we're going to do, what we want to do, is to try to get each of these atoms the same number. So if I look here, I'm looking at sodium. My sodium is 1, and my sodium here is 1. So it's okay, we're good here. So both of them are the same number. So let's look at the second one. I have chlorine that's 2 here, and I have chlorine that's 1 on the product side. So we are trying to make that the same number as well. So as I said, we're going to use coefficients, and by adding coefficients, we could try to make them the same number. So what coefficient do I use? Well, I'm going to put a 2 here. By putting a 2 here, this 2 will now say that I have 2 chlorines, okay? But this 2 also affects sodium. All right, so here I have 2 sodiums. All right, it's like, wow, oh no, I messed up the number of sodiums. It's okay, we could always try to go back. We could fix this, right? And so then in that case, then we could go back to the reactant side. And so if I add a 2 here, then now I have 2 sodiums. So what do we have now? Well, I have the same number of sodiums on both sides. I have 2 sodiums and 2 sodiums, and I have the same number of chlorines or chlorides on both sides. Chlorine, really, on both sides. 2, 2. All right. Now, the only thing to note, if you have something that's blank, it's an understood 1. All right. You don't have to necessarily put 1 there, but it's an understood 1. Okay. And so this is the balanced chemical reaction of this compound here. All right. Let's kind of do another example just for just because. All right, just try something just a little bit harder, so that way we could practice more. Okay, so let's say that we have sodium bicarbonate. All right, it's a solid, and it breaks down by heat. All right, so heat it up, breaks down, becomes sodium carbonate, solid, and you get liquid water plus some gas. Okay, so CO2 gas. Now what we want to do, we want to balance this. Okay, so I'm going to put my dashes to the side here, so that way those are my areas of where I'm going to put my coefficients. So now I'm going to split this up, and just like always, I'm going to count up each of the elements. So I'm going to see how many sodiums I have. So on my left side, I have 1 sodium. Okay, I'm going to see how much hydrogens I have. I have 1 hydrogen. How many carbons I have? I want 1 carbon. And how many oxygens I have? I have 3 oxygens. So let's do the same thing on the other side. So sodium on the other side, I have 2 sodiums. For my hydrogen, all right, I have 2 hydrogens. For my carbon, I have just 1 carbon. And then for my oxygen, so oxygen is kind of funky here. There's 3 here, there's 1 here, and there's 2 here. We add them up. So 3, 1, 4, 4 plus 2, 6. So I have 6 oxygens. All right, so Now, when we're looking at this, oh, I just realized I don't have one carbon. I actually have two carbons. I apologize. There you go. Now this becomes so much easier. Okay, so now when you're looking at our numbers, right? So one sodium, two sodium, one hydrogen, two hydrogen, one carbon, two carbon, three oxygens, six oxygens. All right, there's only one reactant here, and then we got three products here. So in the beginning, it almost seems complicated, but I think once you figure out your numbers, it's like, oh, this shouldn't be too bad, right? Because when you hopefully you notice that all you really need is a 2 here as a coefficient. When you have 2 here, this sodium becomes 2 because you distribute this 2 to all the elements here. Hydrogen now is 2. Carbon is now is 2. You used to have 3 oxygens. Now you have, can't write. Now you have 6 oxygens, right? And so everything matches up accordingly. So now I have a balanced chemical reaction. All I needed was a 2 there. Now you don't have to if you don't want to, but remember these blanks are just understood 1. Okay. Now let's do let's look at one more example. Okay. So let's say that we have H2SO4 plus NaOH yields Na2SO4 plus H2O. All right, so this is the equation that we're going to balance now. All right, so I'm going to go ahead separate them out, and I'm going to count out each one to see what I got. So I see I have H, I have 2 here, 1 there, so I have 3 H's. All right, I have my sulfur, I got just 1 there. Then I got oxygen, I have 4 here and 1 there, so 5 oxygens. And then I got sodium, and I only got 1. Okay, so let's do the same thing on the other side. I try to keep everything in the same order. So hydrogen, I see I have 2 here. Sulfur, I have 1. Oxygen, I have 4 here plus 1. So that's 5. And then for sodium, you notice I have 2. Okay, so now I'm going to go ahead and balance this out. Now, one of the things, it's kind of just the trick of the trade here. It's just one of the things I just noticed as we go through these type of chemical reactions, is that hydrogen, typically we notice I've always start with the first element I've listed, okay? But in this case, I won't do that, all right? Because for hydrogen shows up in 2 different places in the same side. So that's just going to make things kind of a little bit complicated. And so I'm going to kind of look for something that only shows up once and then see if I could kind of figure things out from there, all right? So like hydrogen starts at 2 different places. Hydrogen here is only 1. So I notice my sodium on both sides are only in one spot of each of the sides of the chemical reaction. So I think I'm going to actually start with sodium and just kind of move around. You could actually just pick whatever element you really want to start with. But it's just one of the things I've noticed. Some are easier to start with than others. But you won't really know that until you try. This method of balancing chemical reactions is really just trial and error. You try. If you messed up, you just try again. And if you mess up, you erase and you try again. All right. So you just try numbers until it works, really. So, you could have a chemical equation legit, you start off, it could take you 10 seconds to solve or 15 minutes. Because due to the trial and error type of thought mentality. But anyways, so I'm going to start with sodium, right? And as I said, I noticed sodium, there's only 1 here, there's 2 here. So what I'm going to do, I'm going to put a 2 here, all right? This 2 will make it that I have 2 sodiums now, but this 2 is going to be also distributed to all the others, okay? So now let's go ahead and calculate how many of each of them that we have. So I see now this makes it have 2 oxygens, right? But remember, I already had 4 oxygens here. So it's 4 oxygen plus 2 oxygens. So now I have really 6 oxygens. Okay. The 2 also affected my hydrogen, right? Now I have 2 hydrogens here, right? And I already had 2 here. So 2 plus 2. So in this case, I have 4 hydrogens. Okay, and that's about it. So it doesn't affect my sulfur. So now let's go to the other side. Let's see if we could fix a thing or two to try to make this good. So I have 4 hydrogens here. I have 2 hydrogens here. The cool thing about this hydrogen, there's only hydrogen in one area here. So then if I put a 2 here, right, then this will become 4 hydrogens. But this also affects my oxygens. So I have 2 oxygens here. I already have 4 oxygens here. So 4 plus 2 is now 6. Okay. So do we have ourselves a balanced chemical equation? Well, yes, we do. Remember, now all your blanks, as I said, are understood ones. All right. So it's a 1, 2, 1, 2. All right. Now, just a rule of thought, balanced chemical equations, you always want to make sure that the coefficients are reduced to the lowest whole number values. So what do I mean by that? Like, so if you look at this chemical equation here, right, H2SO4 plus NaOH yields Na2SO4 plus H2O. If you got answers 2, 4, 2, 4, well, this is technically correct. It is balanced. You will have the same number of each type of atoms on both sides of the reaction. All right, but the coefficients are not the lowest whole number ratios as possible. So typically we like it the lowest whole number ratios. And so in this case, the correct answer would have been just 1, 2, 1, 2. Now, if you end up finding that if you're balancing a chemical equation and that you come up with this just due to the process, then if you notice, okay, you're not going to simplify the numbers, then go ahead, simplify it. That will work, okay? And then the good thing about trial and error is that you can always just double check and just to make sure you have the right amount. So like, for example, in this case here, how do I make sure I have the correct coefficients? Well, count them through, right? How many hydrogens do you have? Well, I have 4 here, 4 on this side, right? And I have 4 over here, so then I have 8 hydrogens, all right? How many sulfurs do we have? Well, I have 2 sulfurs here. How many oxygens do we have? Well, I have 8 oxygens on this side. I have 4 oxygens on this side. So 8 plus 4 gives me 12 oxygens. All right. And then how many sodiums I have? Well, I have 4 sodiums from over here. Okay. So now let's go ahead and look on the opposite, the other side of the reaction. Let's go ahead and look at our products. So how many hydrogens do we have? Look, well, on this side, I have 8 hydrogens. How many sulfurs do I have? Well, let's look at this with this sulfur here. I have 2 sulfurs. How many oxygens I have? Well, 2 times 4, so that's 8 oxygens here. And then 4 and for this 1 oxygen, so 8 plus 4 oxygens gives me 12 oxygens. And then lastly, let's look at sodium. All right. So how many sodiums I have? Well, I have this 2 here, this sodium, and there's a 2 as a subscript. So 2 times 2 is 4. So I have 4 sodiums here. So now if you look and you pay attention, it's like, oh, all my numbers match up. So then I did this correctly. Okay. As I said, of course, in this scenario, the coefficients, I could simplify them more, but you always just want to double check to make sure your coefficients are correct, that you use the right ones. And then if you have to, simplify. Okay, so this is balancing chemical reactions.